All right, hi guys. So it's been a little bit since we looked at our notebook, but I thought it might be good for some of you if you want to stay organized. So I posted the divider if you want to add that in right after the pages that we did about circles. So I told you how to print this. I think it's page 10 you want to print out, and then you just fold that over like normal. And then the first thing we talked about was the polygon sum theorem, and I put that right on 109. So we got that right here, where I did this little thingy of fun. And then we got a whole list of the quadrilaterals. So I went through that whole PowerPoint of all their different properties. So parallelograms, rectangle, rhombus, square, trapezoid, isosceles trap, right trap, and kite. And I had you guys take some notes and put them on those little flippy sheets, and I put those on 110 and then 111. I was able to fit them all there, and if you need to go to another page, like, that's fine too. And so then what I'm going to add today on page 112, and like ignore my craziness here because I was going to have you guys do some things and I cut them out, but on 112 we're going to add this new one today, and we're going to talk about putting these quadrilaterals on a coordinate grid and how we can determine which precise quadrilateral they are. Okay, so we have a different ways that we can approach this. So one way to determine whether something is a parallelogram or not is by using our slope formula. So if you remember, we find slope by doing y minus y over x minus x. Or, I mean, if we're looking at a graph, really just rise over run. So if we take a look inside here, just to make things a little quicker, I already plotted these points. So if you need to take a pause and plot them, then come back, that's fine. But we're going to want to find the slopes of all of our lines here. And so we really have 4 lines that we need to find. So I just start with A, and I'm like, okay, I'm going to find the slope of line AB, and then BC, and then CD, and then DA. So I kind of just work my way around the quadrilateral to make sure that I get all my lines. And then really to find the slopes, like, you can look at the ordered pairs up here and do that and like do y minus y over x minus x, but for me I usually just count. So if I'm doing AB, I want to start at A because it's leftmost, and I would rise 3 and run 1, so my slope is 3. For BC, I would start at B because it's leftmost, and I am rising 0 and running 4, but it doesn't really matter because 0 over anything is always 0. Now with line CD, I wrote it as CD, but I actually want to start at D because it's leftmost, and when I count from D to C, I have to go up 3, right 1, so up 3, positive, right 1, positive, so slope of 3. And then DA, I really have to start at A because it's leftmost, even though I wrote it like this, and I would go rise 0, run 4 again, but it doesn't really matter because 0 over 4 reduces to 0. Okay, so this is a nice way to prove that this is in fact a parallelogram, because AB and CD have the same slope of 3, and BC and DA have the same slope of 0. And by definition, a parallelogram has 2 pairs of, oh my gosh, it's 2, but I meant 0. By definition, a parallelogram has 2 pairs of parallel lines, so a pair and a pair. And that's why I wrote down the 2, but I meant 0. Oops. If you don't like slope, another way that we could determine if something is a parallelogram or not is by using the distance formula. Now, the distance formula we talked about like super briefly. It's like x minus x squared plus y minus y squared, all square rooted. It's a crazy funky thing like that. There's too many pluses and minuses for me. So really the shortcut version is just the Pythagorean theorem. Like, we're really just doing c squared equals a squared plus b squared, where a and b are our rise and our run. So we do rise squared, run squared, and we square root all of it to get c by itself. So that's kind of the shortcut that I like to use here. And it's super nice because if we were doing the same parallelogram, like I have my rise and run, and I could just get the distance formula quickly. But if we do that in here, now I did change point D. I flipped it just so that it would work out. So if you need to take a minute again to graph that guy, but what we're going to do is we're going to find the distance of each line, because I know by definition of a parallelogram, not only are two opposite sides parallel, or two pairs of opposite parallel sides, but also those opposite sides should be the same length, and distance is length. So just like with the last one, we're going to want to do all four lines, and instead of simply finding the slope, we're going to actually find the length of them. So starting with AB, like AB is just a flat horizontal line, so we can just count that it's 1, 2, 3, 4 long, so that's super nice. But like if you think about rise run, like it's rise 0, so 0 squared is 0, and it's 4 squared, so 16, but then square rooted, so 4, so it still works out. Now with BC, I'm going to count my rise run, so I'm going to square root the rise, which is 3 squared, plus the run, which is 1 squared, and so you're going to get 9 plus 1 for the square root of 10. Now I don't know the square root of 10, it's like a little more than 3, but I'm just going to leave it like that. And then CD, I can count that one as well because it's just horizontal, so 1, 2, 3, 4, length of 4. It's looking good because we got a pair right here that are equal. And then for DA, we want to do that slope again, or the distance formula rather, so square root of rise squared plus run squared. So if I count the rise, I went up 3, and the run, I went 1. And even if it was negative, it wouldn't matter because they would like square to a positive, so you get that square root of 10 again. So this is a parallelogram, and I can tell because AB is the same as CD, like they're both 4, and I can tell because BC is the same as DA. They're both the square root of 10. I don't know exactly how much that is, but it doesn't matter because they're the same. Okay, so another way that we could do that is by showing both slope and distance, which seems like overkill, but I mean, it's fine. Because when I have the slope, I can easily find the distance. So we'll do AB, BC, CD, and AD. So if I first find the slopes of all of them, from A to B, I want to start at A because it's leftmost, and I would go down 1, 2, 3, 4, 5, over to the right 1. So we got a slope of -5. Then to find the distance or length, you have to go all the way back to your original rise run. You have to use these numbers, and you're going to want to square them. So -5 squared plus 1 squared is going to be 25 plus 1, so the square root of 26. Okay, so we can also do that for BC, and I'm going to start at B, and if I count to C, I have to go down 1, 2, 3, and then right 1, 2, 3, 4. And so the slope is -3/4, and then when I do the distance, we're going to square each of those, so square -3 and 4, so we get 9 and 16 for 25. Oh my word, that's 5. I squished this in here too small. I wrote that on the outside flap. E. Okay, 5. CD. I'm actually going to start at D and count to C, and I go down 1, 2, 3, 4, 5, and right 1, so I get that -5 again. There's really no need to go and do it again. Like, these are the same numbers, so I know that that length is going to be square root of 26. And then with AD, if I count that slope, I want to start at A because it's leftmost, and I'm going to go down 1, 2, 3, and then right 1, 2, 3, 4, so I get that same slope of -3/4 as AB, so I know that that length is going to be 5 as well. So parallelogram for sure, because two pairs of opposite parallel slopes and lengths. Okay, so on the last one, you can actually use a midpoint formula to prove that something is a parallelogram or not. And you don't use the sides of the parallelogram anymore, because something that is true about a parallelogram is that the diagonals bisect each other, so they should have the same midpoint. So your midpoint formula, we had a formula for it where you like add up your x's and take half, you add up your y's and take half. But we also talked about you do rise over run, but then go halfway. So, I mean, same sort of idea, like you can hopefully kind of see that in the formula. Rise and run, but we do half, and you can see the halves here. Okay. So I graphed this one and I hate it already because I didn't do a parallelogram. But that's okay, we can change it after the fact. So instead of actually doing the side lengths, what you do instead, and I wish maybe this is a different color, you connect the diagonals, and we're going to look at those instead, because we know some things about the diagonals, and if those things are true, then we know it's a parallelogram. Like in a parallelogram, diagonals must cut each other in half. So if I take a look at the diagonal AC and find that midpoint, if it had the same midpoint as DB, then I would know that they bisect each other and it's a parallelogram. But I mean, like, it definitely looks like not. So to find the midpoint of AC, I would start at C and count to A. So I have to go up 2 and then over 1, 2, 3, 4, 5, 6. But not really, because I want to do half of that. So I want to do 1, 3. So I'm going to go up 1 over 1, 2, 3. Oh my god, what an unstraight line. Ah! So the midpoint of that is at this point here, which is at 0, 2, because it's over 0 and then up 2. And then DB, oh my god, this is awful. I would start at D and go down 2 over 2 to the right. So instead I'm going to do down 1 over 1. That's a better looking line. But since that midpoint is at 0, 3 and they're not the same midpoint, it's not a parallelogram. But I feel like it's good to sometimes see a not example, so that's fine. Alrighty, so another thing that we can do is talk about rectangles. Okay, so we can determine that something is a rectangle by using the slope formula or the distance formula like we were talking about. So I have my rectangles here. And on this first half and the left half, we can determine if both pairs of opposite sides have slopes that are perpendicular to each other. So I really need to know all the slopes, and we want to know that it's a parallelogram, so like opposite slopes are the same, but we also need to know that right here we have a 90. Because if you have a 90, then you definitely have a rectangle. So we're just going to find all the slopes again. So slope of AB, BC, CD, DA. And the slope of a horizontal line is always 0. The slope of a vertical line is always undefined. CD is horizontal, so 0. And that one's vertical, so undefined. And horizontal and vertical lines are always perpendicular to each other. So because they are, you have a rectangle. Now another way to do it, because that feels kind of cheaty, and like sometimes when they're slanted rectangles, it's a little bit more satisfying to do. But we can also use the distance formula by proving that it's a parallelogram and then determining if the diagonals are congruent. So to show that it's a parallelogram, I can show that the slopes are the same. So I know that AB has the same slope as DC, and it's both 0, so like we just did that here. And then BC has the same slope as DA because they were both undefined. So that tells me I'm a parallelogram. And a rectangle is a parallelogram as long as the diagonals are the same length, because that is a property that it has. So if I draw those diagonals in, I can find the length of AC and DB by doing rise squared plus run squared and then square rooted. So from A to C, I would go down 1, 2, 3, 4, and then over 1, 2, 3, 4, 5, 6. So 4 squared plus 6 squared is going to be 16 plus 36, so 52. And then for DB, I'm going to start at D, and I would go up 1, 2, 3, 4, and over 1, 2, 3, 4, 5, 6, and look at that. You get the same two numbers, so like math is easy because it's the same, and so square root of 52. So since the diags are congruent, it's a rectangle. Now, just because of time, like this is already a long video, I'm not going to do the ones inside, but if you guys want to, you can. So on the inside there, like you can connect and make a rectangle, and I can either show, and this one would be a little bit more exciting, with the slopes, that this slope and this slope are perpendicular to each other, which is opposite reciprocal slopes. Or I can draw in the diagonal and show that the diagonals are the same distance. You can do that with this bottom one as well. And I'll post the answers to that too if you do try them. Okay, because I want to try one last one where we're talking about squares. Now, on this squares and rhombus one, this prove it down here, we are so done with proofs, so not sis, we're not doing that. But up here, we can draw our shape. So I plot all those points, and just by looking at it, you probably have a guess as to what it is, but you need to show that it is what it is. So I first need to show that it's a rectangle, and I could do that by drawing in the diagonals. And finding that they are the same length. So I'm going to do that. So BD and CA. So the length of BD, I'm going to count my slope. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So square root of 6 squared plus 6 squared is going to be the square root of 72. But I mean, if I have two 36s right here, I can really just write it like that. So it's going to be 6 root 2. A little 45, 45, 90 action. And then for CA, counting from A to C, I would go up 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4, 5, 6. So it's the same thing. So 6 root 2. So I know that it's a rectangle because the diagonals are congruent. And I can also show that it's a rhombus. And to know that something is a rhombus, it has to have all congruent sides. So I can find the length of AB, BC, CD, and AD. And it's super easy to find the lengths of these ones anyways because they're all horizontal and vertical lines, so I can just count, and they're all 6. So it's a rhombus. And so then, once I know that it's a rhombus and a rectangle, I know that it's a square. So yes, because it's a rectangle and rhombus. Okay, so on the inside here, I'll probably leave this one for you to try, but if we take a look at this one, first I want to show that it's a rectangle. I'm just going to stick with the diagonal thing because like it's less stuff to find. So if I draw in the diagonals here, I can find the length of AC and BD. And it's actually super nice because they're horizontal and vertical, and I can just count. Like AC is 4 units long and BD is 4 units long. So yes, it's a rectangle because their diagonals are congruent. Then I need to show that it's a rhombus, and the main fun fact about a rhombus is that all the sides are congruent. So this is going to take a little bit longer, but we're going to find the length of all the sides. So AB, BC, BD, AD. So if I count rise run, I'm going to go up 2 over 2. So square root of 2 squared plus 2 squared. And guys, I don't know if you're remembering the 45, 45, 90 thing, but if I have two sides that are the same on a right triangle, It's a 45, 45, 90. So if this length is 2, that length is 2, your distance is 2 root 2. And so BC, I got 2, 2, so 2 root 2. I'm going down 2 over 2, so 2 root 2. And AD as well, 2, 2, so 2 root 2. So all sides are congruent. Makes me, yes, a rhombus. And so because I am a rhombus and a rectangle, I'm a square. Okay, so totally up to you. You can do the little examples that I left for you in here, or you can just move on to the homework. Either way is fine. But yeah, good luck, and hopefully it goes well.